Hello everybody, and welcome to part 2 of our GPS GNSS testing series brought to you by Heedra and Aurelia. So last session we looked at basically overview of what a simulator and that was, and also how to create a basic test. This week we're going to have a little bit more detail about what a GNSS simulator is, and then getting to how we would tailor tests, if you like, for your particular requirements, so that you can have the test set up as you need. Okay. So first of all, let's look at simulators. So what is a GNSS simulator? So very basically, it's a signal generator which generates RF signals with software designed to test GNSS devices. High quality RF signal generator needs to be very high quality because it's trying to generate signals at very, very low power, minus 130 dBm, around about a trillionth of a watt. And relatively complex modeling software that needs to be very good, that we can create the environment with, and then models that will run to do all the things that we need. Okay, so this is how we can test GNSS device operation. So the first thing I want to talk about is a little bit about simulators. So simulators have been around for a while now. The first sort of systems really date back to sort of the late 80s, and when GPS was really in its infancy, before there was a proper constellation. And from then onwards, they've obviously evolved. They've got smaller, more powerful, but typically they are bespoke hardware that is created, designed specifically, if you like, for GNSS signal generation. It's quite a heavy lot of work to do to create them. It's a lot of manpower for the design, and you have to design custom hardware to do it all. You have to program up FPGAs, you have to write the software to do all the modeling, and this market is not particularly large, so there's a lot of engineering and development effort to be done for these things, plus a relatively small numbers to be manufactured. So the development cost is high per system, and the manufacturing cost is high. What's happened with the Heedra Skydel approach is that we've moved to an open software-defined architecture. So Skydel, which is the Skydel system from Aurelia, is really just a software simulator, okay? And then you use off-the-shelf hardware like software-defined radios, GPU, graphic processing units, which will then do all of the work required that used to require bespoke hardware. This gives a lot of flexibility, a lot of scalability. It allows the software, if you like, process to move forward much more rapidly. It allows new features and new capabilities to be added pretty quickly and very, very prompt, very well. It's not limited by the hardware design, because there are multiple different types of hardware out there. You can generate hundreds of signals in one graphics card, so you can simulate like all in view satellites very easily. In the sort of 200 or so signals per sort of relatively strong graphics card. And the graphics cards, the SDRs, are produced in mass production because they are for used by various different industries, and so they're made in much bigger numbers, and they're general purpose. So there's a lot of economy of scale there. So you get very, very, very powerful hardware, very powerful systems at a sort of fraction of the price of the traditional ways, and this gives you incredible value, and it allows your system to be future-proofed. So let's have a look at basic test requirements, and this is kind of a little bit of a rundown what we did at the end of last week. Basically, what does a test consist of? Well, it's date and time, it's the atmospheric conditions, it's the constellations, where the vehicle's going, visibility of the sky, antenna patterns, terrain, blockages, things like that. any error conditions, and then these settings are stored together in what's called a scenario. Okay, so let's just quickly recap. We'll create and run a basic scenario. So using the Skydel software, we'll create a basic scenario. We'll have a obviously start date, the atmosphere, constellation, use a relatively static trajectory, and then press OK, and then get started. So if we just move on, so let's have this quick demo. I'll switch to the Skydel software now. Hopefully that's changed. So let's have a look at the software. Well, this is as the software comes in. You can see nothing is set up. No outputs are set up. So the first thing we have to do is decide where we're going to output this. So here is where we select our output device, which would typically be something like an SDR. These here are SDRs, the X300 and 310 or DTA 2115B. They're all different types of SDR. Or you can output to a file. You can have no output at all, or what I'm going to select now, no running in real time. So this allows you to play with the system, try the system out, see how things work. Okay, so what I'm going to do is add one of those outputs. So I do that, press the add button, and now you can see we've got one output here. There's no signals defined. If I edit that, you can see now it asks me whether I want upper band signals, lower band signals, or interference. I'll go with upper band. We'll set a GPS constellation or GPS L1 signals. We'll have some GLONASS, and let's have some Galileo as well. And then we'll click OK. Now you see we have constellations here. We have a sky plot. We can see the GPS signals here. We can see the GLONASS signals here. And we can see the Galileo signals here. Okay. The next thing we probably want to do is have a start date and time. There's a default here, which is June the 21st in 2018. We can just set the current computer time if we want. We should set that up. And then, that's that. Relatively easy. Then we may want to set up some global conditions. So this is where we would set up the atmosphere. So this is where we can set up what's in the troposphere, what is the ionosphere. The troposphere, you've got different selections. STANAG is quite common because that's the NATO standardization agreement. Klobuchar is the GPS model, or you can have a space model. Okay, and then we'll go back to settings again. Then we may want to set up something, we may want to introduce a new constellation. We can import a constellation from a UMA or a Rhinex file or something like that. Or we can just go with the defaults. And typically that's it. So we've got it. The other thing we might want to set is the vehicle position. So this is where it's set at the moment, which is somewhere between, somewhere near the US-Canadian border. If I edit that, you can see it gives me a rough view of the world and where it is. If I go move it, I'm in the UK at the moment, so let's have it somewhere in the UK, somewhere around about the middle somewhere. And then I can zoom in a little to get more detail to see where I might want to put it. So let's have it near Milton Keynes. We can zoom in quite a lot if we want. We're somewhere in the middle of Milton Keynes, and we'll say OK on that. No, we won't. We'll use that position, so that presses that. You can see the lat, long, and height's changed, and then we'll press OK. Now we got that. You can see the constellations changed because we're in a different location. Okay. We may want to set an antenna pattern for the vehicle. If we go in here, this will show you the mask, if you like, and you can see different values here for the attenuation. If you want to bring a new one in, you just import a CSV file, or you can export this as a CSV file. Cancel that. Okay, so now we'll go back to settings, and we can run this scenario. You can see the start button's highlighted, it's ready. Press start. System goes away and thinks for a second. Now it's off and going. Okay, you can see here the spectrum we're generating, and I can make that a little bit clearer. The blue line is the Galileo signal. The green line here is the GPS L1 signal. And the red line here is the GLONASS signal. Sorry, we can see it's at a slightly higher frequency, which is where it should be. Here you can see the constellation's mass. You can look at them individually. So here's the GPS signals, here's the GLONASS signals, the Galileo signals, and so on. Okay, and that's very simply it. If I put the map up, you can see that we're locating somewhere in Milton Keynes, and that's where we are. Okay, so if I now stop this scenario, press the stop button, and we will then move back to the slides so that you can see, we can go on to the next stage of the course. So let's have a look at tailoring. So that scenario we just created there is great. It's clean, it'll give you a good position fix, you can see the receiver works, but it's not going to tell you a lot about how the receiver copes in different conditions and things like that. So typically we would want to tailor scenarios so that they do things that they're more bespoke, if you like, for our requirements. So the way to do this is to first of all have a test with perfect conditions. You've got clean orbits, there's no errors, the atmospheric effects, so the Globochar models and all that match what the receiver's seeing, so you don't have any problems there. You have either a very slow or static vehicle. You have a clear sky view. You don't impose any blockages. You don't have any multipath. Everything is good as it can get. And then you can get a measure of your receiver. You may want to play around with the constellations a little bit, so the satellites are all in great positions and everything else. But this will give you a clear measure, if you like, of your receiver capability. And then you want to start looking at where the receiver is going to be used. So, if you can see this guy here, he's down in the woods. He's trying to do a bit of surveying by the looks of it. And, it's not a great location for a receiver. He's going to have foliage in the way, which is going to attenuate the signal. He's got trees and terrain around him, which is going to cause reflections and blockages. And, it's not going to be great. But that's maybe the environment that they want to see how that receiver performs in. A receiver that works great in a clear environment may not work so well there. And if your requirement is that you're going to be constantly in that kind of environment, you want to make sure it's good for that environment. So what you do next is you start to make effects on the receiver. And you do that by changing parameters in the scenario. And when you change the parameters, then you remeasure the PVT solution, you remeasure things like how quickly it fixes, how accurate its position is, how sensitive it is to signals, etc., etc. You measure those things and you see how well your receiver is performing. The sort of things you'd like to change may be geometry, so you might want to do that by changing DOP or putting in blockages. You may want to look at constellation errors. You may want to put some satellites out of position. You may want to play with the atmosphere and put in some delays on the signal so it looks like there's some sun activity. You may want to put high velocities on there or high turns and things like that to see how receiver keeps track if it's moving fast or changing direction suddenly. You may want to play around with the antenna. You can see this guy here. His antenna is on the top of his pole here, so he's not blocking it there. But if the antenna was here, he himself would be a blockage for the signals. You may want to play with multipath so that you can see how your receiver copes with multipath and whether it ignores it or it affects its position. You may want to look at signal power levels and many, many other conditions, interference, spoofing, all that kind of stuff. So just to give you a sort of an idea of what I'm talking about here, so here we've got a look at DOP. So DOP stands for dilution of precision, and generally, if you want to get your receiver have a good chance of getting a good position, you want to have nicely spaced satellites so that they're on the horizon or close to the horizon, maybe one or two above you, but you need to have a good distance between satellites so that you can get a good cross on the ranges from them, and that will give you a good positional fix. If you look at the top here, this is a reasonable fix here with satellites near the horizon and one right above you, nicely spaced, nice effect. Then you may want to see how it copes with poor geometry. So here's not such a good geometry. All the satellites are typically coming from a similar direction. They'll be coming down. The crossover won't be so good. It'll be harder for the receiver to calculate where these lines are crossing and how well the position. So the position will not be as good. It's as simple as that. So if we do that demo now, we'll move over to the Skydel software, and we'll look at geometry. So if we go to the GPS signals here, you can see at the moment they're not bad, but they're not brilliant. I'm going to try and change those a little bit by putting a different time in, and here you can see now they're nicer spaced. There's some around the horizon, a couple above. Okay, if I want to change those, so I can go to the signal tab here, and I can switch satellites on and off. You can see number 10 is here. If I want a good dot, I probably want to think about switching off maybe number 12 and maybe number 19. Let's do that. Let's switch off 12, switch off 19, and now we've got nice satellites around the horizon, one nicely nearly above us, and that will give us a reasonable dot. You can see the dot values here, something like p dot 1.22, something like that. Now if I switch those two back on, and then start switching off some of these around the horizon. I can't switch them all off, but I can maybe switch 10, 32, 17, and 15. So let's switch those off. 10, 15, 17, and let's go for 32. Now you'll see the dots changed. It's a higher number. It's not so good. And the satellites are all in a line. They're not quite all above you, but they're not great there. And that will not give you such a good position. Okay, and that's typically the sorts of things you would do to give you a poor dot or a good dot, and you can see how things work. Okay, so if we go back to the slides now. Okay, so another thing you might want to play with is multipath. Okay, so multipath will affect signals. If you look at the picture here, you can see the direct signal coming in, but you've also got a reflection there. Again here you've got a direct signal plus a couple of reflections. That one's being very greedy. And reflections will make it harder for the receiver to track the signal. Okay, if you've got a direct signal and a reflected signal, effectively you've got two signals slightly delayed, so the peak will not be as sharp in its algorithms where it's trying to detect the range, and it will make it harder for the receiver to calculate the exact range. One reflection isn't always terrible because typically the signal is polarized, so it's circularly polarized. It's right-hand circular polarized, so when it reflects, it bounces off as a left-hand polarized. If you've got an antenna that's tuned for right-hand polarization, it will lower the signal power if it's left-hand. But then if it reflects twice, double reflection, it goes back to right-hand, and that can have an effect. And these are the sort of things you need to think about. So let's just quickly look at how we do multipath in the software. Okay, so I'll set all these signals back on. So all of them back on now. And then you can see there's a button here, all nicely laid out, multipath. So let's look at the satellite that's there, number 10. So we'll take this to number 10. And we'll see what we can do with number 10. So let's put a reflection on. Let's put a range error on the pseudo range. Let's put some, see 8-meter range error. Let's put a power offset, maybe 12 dBs. And now you can see we've done that. Let's maybe put a second reflection on there. Let's again put a a bigger range. Maybe this is a double reflector, but then that will be less of a power offset because it's not affected so much. Okay. Maybe we want to do another one. Let's do another one. Let's go to 15, and then we'll put an echo on here. Let's maybe 8 power loss. Okay, maybe a power loss there, and then we'll do that. Okay, now we can see. Sorry, cancel that. I didn't mean to press that one. Now we can see a summary. We've got 2 reflections on 10, 1 on 15, and that's what that's done. Okay, relatively simple. We can start running it now if we want. We can see the effects of that. It's, obviously it would only show in the receiver. It's not going to really notice it in these. And there you go. Okay, so let's stop that again. And then let's go back to the slides. Okay, so that's just to give you an idea of the sorts of things that you can do when you're playing with scenarios. Now, obviously, there's a lot more you can do, and I'm not going to take you through everything here and now. What I really want to show you now is about automation, how you can automate that so it does the same things every time. Obviously, it's really great to have the flexibility to click your mouse and make some changes so that the scenario does these things. But the next time you run it, it probably won't happen at the same point in time. So that's not so good. So what we need to do is to save, if you like, those controls, maybe even edit those controls so that we can have a repeatable test that we can run again and again. And repeatable tests is what it's all about. So that's what the Automate does. So if we, talk a little bit about this, what Automate does is it records what you do when you're using the software. You can save it to a file, and it's a text file, so you can go in and edit it if you want. Or you can save it to a Python script. You can, say, edit it so things happen at the same time or at different times, or you can add more in, take things out. All those kind of things. It replays then that condition again and again and again, and the scenarios can be run standalone as a Python application. So let's do a quick demo of creating a script. So I'll go back to the software, and the first thing I need to do here is go into the Automate. You can see we do stuff, and I'll clear that so that we don't mess around with it. Okay. So now there's nothing in there. We've got, we'll go to the settings, we'll look at multipath, we'll disable the echoes, we'll switch them all off so that we've got nothing in the pipeline anymore. So they're all disabled. If you look at summary, they're there, but they've all been switched off. Okay, so 15's off, 10 is off. Okay, and then we'll start the scenario. Let's start it running. Okay, so we're running now. We can do something like we can drag the power down on this one, maybe take the power up on this one, that kind of thing. We can switch on a reflection, so I switch that one on, and and it's running. Maybe we want to do some other things. We won't do that now. But I'll stop this now, and then you can have a quick look. You see the spectrum there is being generated. You see those changes. Stop. Okay. Now if we go to Automate, you'll see it's recorded what I did. Did a start. It's changed the power levels, switched on a multipath, and then it stopped. Okay. I've got a button over here called Run. I can press that, and it starts running. Okay, if I go to settings, you'll see the multipath there. You can see it's changing the power levels. I'm not touching anything. Got my hands off the mouse. See it's doing those changes. In a second, it will click on the echo. There it goes. And so what I did now, I can run that again and again and again, and it will do those same things. Okay, so whatever you set becomes a repeatable test, and then if you want, you can edit that file, change it, and do things to it. So I'll stop that now. I'll look at automate again. You can see it's there. I've stopped it again because I did a second stop. And that now, if you want, you can export it as a Python. You can save it as a file, and it's there. Okay. If you want to look at these, you can see it gives you what the things are for each of the commands. Okay. Right. It's a fairly logical script. There is information in the Skydel software to give you more detail on what each of the parameters do. So we'll go back now to the script file, or to the presentation, and we'll just do a summary of that. So first of all, it's all about starting with a simple test and then incrementally add changes, so that then you can see what really affects them. And maybe first of all try multipath, and then take the multipath off, then try power changes, take that off, until you really understand your receiver very well. Then you can use the automate system to control it, and so that then those tests become sort of fixed, and then you can repeat those tests again and again and again. Okay. So that's all I wanted to do in this session. Obviously, there's a lot more playing you can do, and if people need more information on that, please feel free to talk to me. There will be another live session next week on the 2nd of July, which will be more about robust PNT, how to test receiver resilience, testing things like SERPers, and maybe some advanced requirements. Okay. If anyone needs to get in touch, there's my contact details. It's my name, obviously, my email address, and telephone number that you can call me on. Okay. Thank you for listening. I hope it's been useful and interesting.